So to start off, why do we need to look at aluminum alloys and the use of 6000 series as far as aluminum sheets are concerned? So one of the main things that we want to do is to be able to reduce the carbon emissions that are coming from passenger vehicles. One of the things you can do is switch from steel to aluminum sheets as far as the exterior components are considered. So I know a lot of people have seen this image before. This is the Audi A8, where you have a lot of 5000 and 6000 series sheets that are used as the exterior. So one of the things that I'm be focusing on in this entire talk is looking at forming. When you're actually doing the forming operation, you need to have the material in a soft state. So when you go ahead and actually form the material, the part that we'll be looking at is these very sharp bends where you have the very nice designs that the car manufacturing designers want to have so that they look aesthetically appealing and you want people to buy the vehicle. However, when you actually have the products in service, if your child or you open the car door carelessly and hit another car, you don't want to give it a dent. So you really have this dichotomy between when you actually make the door, you want it to be soft. However, once it's in operation, after the paint bake cycle, you want it to be hard. So this has been well studied, and it's all about optimizing the precipitation properties of these alloys. You can do that by adjusting the composition and the processing methods through things such as pre-aging. However, it's this forming aspect that is much less understood. And for this, we need to look at the cluster state of the material, as these materials, after they undergo the solutionizing treatment, they are let to sit for to naturally age, and this is going to form clusters within the material, which is going to affect the plasticity. So in that image where we're actually showing the forming of these materials, you can almost envision those very sharp bends as the diffuse neck region within tensile samples. And so if we actually want to look at this, it's been shown before that for Constellium criterion, which is the onset of diffuse necking, that you want to have an increase in the work hardening rate, and that will delay the onset of necking. And once you actually do form the neck, your local strain rate will increase, and as a result, you'll want to increase the strain rate sensitivity of the material to ideally prolong the onset of local necking. So this project is going from start to finish. So we start off with the compositions. We then look at how the compositions and the different processing methods will then change the microstructure that you form. We can then analyze these microstructures through tensile and strain rate jump tests in order to get our work hardening and strain rate sensitivity properties, and finally how this all leads up into the formability. So between composition and the microstructure, we can either undergo direct natural aging or we can do pre-aging of the materials. We can adjust the compositions of the materials by adding varying levels of silicon, copper, and magnesium, which are going to be the main solute elements in these alloys. We can analyze the microstructure through use of differential scanning calorimetry, small angle X-ray scattering, atom probe tomography, and hardness testing. We can perform the tensile and strain rate jump tests in order to analyze the work hardening and strain rate sensitivity behaviors and how these two interact with each other. We can then see how both of these properties are going to influence the diffuse and local necking behavior of the materials and ultimately lead up into the formability. Now, I don't have time to explain all of that. A lot of it is in the paper. So if you want to, again, refer to that, you can. So I'll be looking at just the copper effects of aluminum 0.35 weight % mag, 0.9 weight % silicon, with 0.2 and 0.8 weight % copper. Under natural aging, we'll do the characterization of DSC and hardness, the tensile and strain rate sensitivity properties, and we'll leave these basically up to there. So in general, what is a DSC curve? So if you haven't used this technique before, you basically put a small piece of aluminum in a certain state within a temperature controlled environment and you increase it at a certain rate. You can effectively determine any of the precipitation or clustering peaks as something that comes up above the x-axis here, and any endothermic reaction is going to be below. So as you can see here, when there's no copper added to the system and we perform the scan in the as-quenched condition, we have clusters that form starting at about 50 degrees Celsius, finishing at around 150, and then we have dissolution starting at around 170. So you can see here the beta double prime peak. This is what you'll be forming during the actual paint bake cycle. And so you can see here it does have quite a strong signal. After you go ahead and let the material naturally age for 30 days, you can see the clusters have already formed, so we're going to be following this, and they begin to dissolve at around 140 degrees Celsius, at which point we have the dissolution of the natural aging clusters. Now, one of the things that you'll notice is that there's an increase in the peak temperature of the beta double prime peak. So as a lot of people have talked about before, this is what is known as the negative natural aging effect in the aluminum alloys. And this is something we do ideally want to avoid if, once we go through the paint bake process, we want to have a hard material. So we can then look at the effects of copper and how these will be changing. So at the top here, you have the as-quenched condition for each of the samples. You can see a minor increase in the clustering peak temperature. and not much is changing as far as the cluster dissolution in the as-quench condition. However, you can see that when you add copper into the system, you almost anchor the beta double prime precipitation peak and shift it to lower temperatures. Things get a little bit more interesting when you naturally age the material for 30 days. You can already see that as you add copper, you get a dissolution of the natural aging clusters earlier, meaning that they're less thermally stable than those without copper. However, you also get the beta double prime precipitation peak that remains much closer to its as-quench value, such that you reduce the negative natural aging effect in the 6000 series when you add the copper. We can then transfer this over and just look at the hardness, and the general thing is as you add copper into the system, you increase the hardness. So we'll be testing these alloys after 30 days of natural aging, and we did that. So we tested these samples, standard tensile samples, 25 millimeter gauge length at a speed of 5 times 10 to the negative 4 per second, and the general trends are as follows. You increase the copper content, you increase the yield stress, and the UTS. The tensile elongation does change a little bit. You do get some increased elongation with copper content as far as uniform elongation is concerned. On the right-hand side here, you have a Cox-Meckingstrom plot, which effectively plots the instantaneous work hardening rate compared to the increase in the flow stress. So you'll basically be looking at the active stress subtracted by the yield strength, and you'll plot that one against each other. And the slope of this curve represents the recovery of dislocations within the material. So one thing that we can say is that as we add copper into the system, it tends to reduce the dislocation recovery behavior, and this is going to aid us in prolonging the formation of a diffuse neck in these materials. So the part I really want to talk about is looking at the strain rate sensitivity. So if we look at the strain rate equation based on an activation energy for dislocations to overcome an obstacle, given that there's a certain amount of thermal energy within the system, we have the rate equation. So we have dislocations that are pushing up against obstacles. These can be clusters, precipitates, or other dislocations. As we change the applied stress, it's possible for these dislocations to overcome these obstacles, and we can calculate out, based on the separation distance and the actual size of these obstacles, the apparent activation area, which if we multiply by the Burgers vector, will give us what's known as the apparent activation volume. However, experimentally, we don't change the applied stress rate. We change the applied strain rate. So we can have it where if we do a partial derivative of this equation, we get where the inverse apparent activation volume is effectively related to the change in the applied stress with respect to the change in the ln of the applied strain rate. And if we plot the evolution of the activation volume, again, versus the subtracted or reduced flow stress, which is sigma minus the yield stress, we can plot this along in what's known as the Hassan plot throughout work hardening. And that would, where the slope of the Hassan plot will give us this thermodynamic strain rate sensitivity parameter S. So something you'll notice, if you have a positive intercept on this on the Hassan plot, that means that the obstacles that are in your system are more thermally activatable than force dislocations, which will have an intercept of 0. The contrary is true, where if you have a negative intercept within the axis, then you have whatever obstacles are in your system controlling deformation are going to be more athermal. So how do you actually go ahead and perform these strain rate sensitivity tests? So on the top, you have the evolution of strain versus time, and on the bottom, stress versus time. Conventionally, all you do is you apply a strain rate, let's call it epsilon dot 1, and you reduce it to epsilon dot 2. That's it. What happens during this transition is that when you do the strain rate change, not only does your machine pulling against the sample, but during the strain rate change, your sample pulls against the machine. And as a result, you have this large transient. And so during this time, you can see that the time it takes between the rate change to the minimum stress value is about 1.5 seconds. And so what's going to be happening during this time is that you're still deforming your sample, you're still producing more and more dislocations, so the delta sigma, or the change in the stress drop that you're measuring, is actually going to be artificially less than what your material should be responding. However, if you add a step into your system, so this is actually, think of it as letting your sample go into free fall during the rate change, you can really reduce this response time down to under 0.5 seconds, and as long as 80% of your total stress drop is occurring within about 50 milliseconds, maybe 100 milliseconds. I'm not exactly sure what the ideal component is. It depends on what obstacles are present in your material. You're able to get much more accurate values. And so we can then go ahead and actually create the Hassan plot. So for the example of down changes, we can look at the true stress and true plastic strain. We apply a certain strain rate, as shown here. We decrease it, and we measure how much the stress changes. Do the same thing if you do change the strain rate by a factor of a quarter. Plot this onto the Hassan plot, and bam, you get your thermodynamic strain rate sensitivity. So we can do this, and I'll show you for an example, at the 0.2 weight percent copper. So don't forget, you can do these strain rate jump tests both by increasing or decreasing the strain rate. So in the case where you actually go ahead and increase the strain rate, what I call up changes, you can see that we have what appears to be two different regions, a nice linear region at the beginning and a relatively flat region towards the end. So this here represents the start of your material. This here is what you're more concerned about in formability, which is towards the neck of your sample. If, on the other hand, we insert these down changes, so we decrease the strain rate and we allow for the compensation to take place, you can see that three regions appear, or at least I'm going to call them three regions. You can call them other things, but for right now, this is what I've been able to identify. At the beginning, you have region 1. During your deformation, what you have in your system, you have, in this case, clusters. This is what's going to be controlling your deformation. In region 2, you've created enough dislocations that these will become your rate controlling obstacles. And I call region 3 based on the separation between the up change and down change. So to sort of think of what is happening within this and how does the activation volume actually come into play when you're actually doing these rate changes, and what is this whole thermal obstacle, and how do you actually probe these things, I've sort of tried to make a schematic to sort of show you how this is changing and how these regions can come into play. So we have a certain amount of thermal energy in the system, KT, represented by the hashed light blue area. And the rate changes are always going to be acting on the rate controlling obstacles. So at yield, the only obstacles we really have present in the material are going to be these clusters. And they largely outweigh in density, the number density of ingrown dislocations. As we begin to deform the material, we increase the dislocation stress such that the total stress increases. And they're going to have a certain activation volume associated with them. We then increase the dislocation density more as we go through work hardening. And as you can see here, the rate controlling obstacles will now become dislocations rather than the clusters. However, there's a difference. If we were to increase the strain rate, then the only amount of thermal energy required to overcome the system is this small area here. However, if we decrease it, we have this larger area. And something you'll notice, if we draw a straight line over to this side, it cuts into the cluster region, such that when you perform the down changes, you're going to be able to actually get effects from both the clusters and the dislocations in the strain rate sensitivity, which is going to be something that may be contributing to the difference between the up change and down changes. And finally, you can keep stressing and keep work hardening your material, and eventually you'll get up to, again, dislocation-dominated regime. So we can then go ahead and look at the differences between the closed circle down changes, open circle up changes for the effects of copper. And as I showed before, we have our cluster-dominated region, where the regions here are more thermally activatable than dislocations. We then have a relatively dislocation-dominated regime, and then we have this change in mechanism that's occurring between the two. So we can summarize this looking at the thermodynamic strain rate sensitivity versus copper content. As you can see here, there's very little effect at the yield strength, or at yield as far as what the strain rate sensitivities of these materials are. So we can say that the cluster content and cluster types are very similar, and they do not show a very large difference within the material. If we go ahead and perform the up changes as we get closer to the neck region, we can see that there's a slight decrease in the up change strain rate sensitivity near failure. However, if we do the down changes, we still have the same trend where increasing copper content decreases the thermodynamic strain rate sensitivity. However, the contrary is true. Rather than decreasing the strain rate sensitivity in terms of up changes, some other mechanism is taking place, which will actually increase the apparent strain rate sensitivity of these materials. And so finally, just in conclusion, we have copper additions are going to increase the clustering signal within the material, which increases yield strength, and we also have an increase in the total work hardening capacity, possibly caused by a decrease in the recovery rate of the dislocations. We have a slight decrease in the strain rate sensitivity at high strains with copper additions, and the most important thing about this work thus far, I feel, is that there's a clear asymmetry between the up change and down change strain rate tests. And how does this all work into formability? So at the very beginning, I showed you that the strain rate sensitivity applies only to the region within the neck. And this is true when you have a strain rate that increases. However, If the strain rate is constant across the entire sample and you have a local increase within the neck, you need to take into account the fact that your strain rate will decrease on the region exterior of the neck. And since we have an asymmetry between these two values, it's possible that you're going to be able to, the increase in hardening within the neck interior is going to be less than the decrease in the softness of the material on the exterior. So the next step for this is really to model the neck formation and how you're able to have neck stabilization, neck propagation, and ideally be able to prolong the neck in these materials. And thank you, and let me know if you have any questions.